Okay, the learning objectives for this section of work is learn and apply the first three laws of logs, which are being indicated below. Find the slope of a function at a given point on the function, and be able to differentiate a complicated logarithmic function by applying the three laws of logs below. You're expected to copy out all the notes and write down the examples and then answer the questions which have been indicated in red below. The expectation is that you will do this over a couple of days. Now, the first thing we're going to do is we're going to look at differentiating y equals 5 to the x. And we're going to be using again the log tables book, formulas and tables book, and specifically we're going to be looking at using this formula here. And what I've done is I've rewritten the formula up here, and then we're just going to basically follow it. So what we have is when we differentiate the y, we get dy by dx. What does the formula tell us? It tells us that whatever we had, we write again. So it's going to be 5 to the power of x. And then we're going to multiply by the log of the base value. And the base value is a, so the base value is 5. So it's log 5. And that's all it is. This second example, in actual fact, is a trick question. You can use your laws of indices to rewrite it. So you end up with 3 over 5 in brackets to the power of x. So now you can use the same formula again. We're going to be using the formula y is equal to a to the x, and dy dx is a to the x times log a. So using the formula, we've got dy dx is equal to a to the x log a. So what's the base? The base is 3 over 5. What's its power? Its power is x. What do we then multiply by? We then multiply by the log of the base number, which is going to be log of 3/5. And that's the end of that one. And again, the same is true here. This is a trick question. You're using your laws of logs, where if you have a common power, you can take that power and put it on the outside of a bracket. As a consequence of that, you can now write this as 2 5s, which is 10 to the power of x. And now when you differentiate, it's going to be dy dx is equal to 10 to the power of x. The exponential doesn't change. And then you multiply by the log of the base number. And that's it. And that's going to be question 6. On page 348. Going to the next page, this is just a little bit more complicated. And the problem is that what we have is we have a power which isn't an x. We have a power which is not an x. So in this situation, it's a lot more complicated and you need to take great care. So we know that y is equal to a to the x is in the formula and tables book. And we know from the formula and tables book that dy dx will now equal a to the x times log a. What we also know is that the question that we have is a lot more complicated. It's y is equal to 7 on 2 to the x plus 5. So we now have x is equal to 2x plus 5. And you should know from previous work that we now differentiate this with respect to x, and we get 2, which will be our multiplying factor. We also know, in comparing it, that the value of a in this problem, let's write it here, is equal to 7. Okay, now we're going to apply it. So we've got dy dx is equal to the exponential, doesn't change, and then we multiply it by the log of its base number, which is 7. And you've got to be careful because you think you're finished, but you haven't, because we have a multiplying factor, and that multiplying factor is 2. Now we're just going to change the order that we're writing this. So we bring the 2 to the front, then we'll bring the ln 7 to the front, and then we'll put 7 to the power of 2x plus 5. Just about squeezed it in, sorry about that. Moving on to the next example. Okay, so what we have is we've got f of x is equal to the natural logarithm of the square root of x squared all over x squared plus 1. And we can't differentiate this at this moment in time because it's not written in power format. So we're now writing it in power format. We've got x squared over x squared plus 1 to the power of a half. Now what we're going to do is we're going to use the power law for logs, and we're going to bring this half down to the front of the log. So we're using the laws of logs to simplify it, and we still haven't differentiated. So we're bringing down 1/2 on the natural logarithm of x squared over x squared plus 1. And what we're going to do now is we're going to use the division law. So we're going to use the division law, and the division law says log of the top minus log of the bottom. So we still are not in a position to, so it's going to be half the log of the top minus 1/2 the log of the bottom. Now I think we can differentiate. So when we differentiate f, it becomes f dashed x. And now we're going to differentiate a log function. Now, hopefully you've learned what was in the previous video, because when we differentiate a log function, then we put this on the bottom. So that's going to be x squared. And we put 2x on top. So we put the what's inside on the bottom, and then we differentiate the bottom, which is 2x, and we put that on top. So here we've got the half at the front, and we're going to be multiplying it by a fraction. What's the rule? We put the x squared plus 1 inside, and then we differentiate this and put the differential on top. And that's the shortcut method for differentiating log functions. The 2 cancels with the 2 cancels with the 2. So we've now got f dashed x is equal to x over x squared, which of course is x times x, minus x over x squared plus 1. And we're still tidying it up because one of the x's on the bottom here will cancel with one of the x's on top. So therefore that now becomes f dashed x is equal to 1 over x minus x over x squared plus 1. Now, the question actually asks us to write it in a particular form. So what we're going to do is we're going to go right back to the top of the page and we're going to continue. So f dashed x is equal to 1 over x minus x over x squared plus 1. When you're adding fractions, to get a common denominator, you multiply the bottoms together. X on x squared plus 1, you've got a minus sign, and this is x on x squared plus 1. And then what have you multiplied the first fraction by? You've multiplied the bottom by this, which means we now have to multiply the top by the same thing. So the top is now going to be multiplied by x squared plus 1. On the other one, what did we multiply the bottom by? We multiplied the bottom by x. So now whatever's on top, which is x, has to be multiplied by the same quantity. So now we can put it into a single fraction, which is x on x squared plus 1. And on top, we've got 1 on x squared plus 1 minus x on x is x squared. So expanding the top, we're going to get x squared plus 1 minus x squared. And expanding the bottom, we're going to get x cubed plus x. When we tidy up the top, the x squared and the minus x squared cancel, so we're left with 1 over x cubed plus x, which was the format they wanted it in, with a number in front of each is equal to 1. That's the end of that example. Going on to this example, it says here find dy dx. And don't forget what we did earlier on, what is dy dx? Dy dx is the slope function. So let's not forget that. Now, it's best not to find dy dx first until we've used the laws of logs. So we're going to use the division law, which is log of 5 minus log of x, because log of a fraction is the log of the top minus the log of the bottom. We're now going to differentiate this to get the slope function. If we differentiate a constant, because that's what log 5 is, just an ordinary number, differential of a constant is 0, minus, how do we differentiate a log function? Well, we create a fraction. Whatever's inside the log goes on the bottom, and then we differentiate this bottom. In this case, we get 1, and we stick it on top. So therefore, the slope function dy dx is now equal to minus 1 over x. This one here, once again, we're going to use the laws of logs before we tackle the problem. We're going to use the power law, and the power law is bring the power to the front. So we've now got this. And we're now going to differentiate, but how do we differentiate a log function? If you've learned what was in the previous work, we've got a 4 at the front, so it's going to be times. How do we differentiate a log function? Whatever's inside the log goes on the bottom, and then we do the differential of the bottom, which is 3, and we write that on top. And then we tidy up by multiplying it out, and dy dx is 4 times 3 is 12 over 3x plus 2, and that's the end of that particular problem there. there. Moving on, we're doing the slope function, or find the slope of the function at x equals 2. So what we're going to do now is, before we differentiate it, we know that the fraction law is going to be the log of a fraction is the log of a top minus the log of the bottom. Now when we differentiate this, we've got dy dx. How do we differentiate a log? We create a fraction. Whatever's inside the log goes on the bottom, and then we differentiate what's inside the log and we stick that on top. Then this one, we create a fraction, and whatever's inside the log goes on the bottom. Then we differentiate that bottom, which is going to be 5. We stick that on top. They asked us to find the slope when x equals 2. So now what we're going to do is we're going to substitute x equals 2 where x is. So it's 3 on 3 bracket 2 plus 2 minus 5 on 5 bracket 2 minus 1. We're going to work this out. So 2 3s are 6. 6 plus 2 is 8. So the first one is 3 over 8 minus 5 over 9. And if you're prudent, you will do this on the calculator. So this is going to be 3 divided by 8 minus 5 divided by 9. And the answer is minus 13 over 72. Minus 13 over 72. Next example. Again, did you spot it was the log of a product? If you spotted it was the log of a product, then you know it's going to be the log of the first plus the log of the second. Before you go any further, did you spot that this is the power law? So now you can bring the power down to the front. So it's 4 log x plus log of sine x. So I've got sine cos minus sine minus cos. Now I'm going to find the slope function, dy dx, and it's going to be equal to 4 times, how do I differentiate a log function? Whatever's inside I put on the bottom, and then I differentiate the bottom. In this case I differentiate x and get 1, and I stick that number on top. Here, whatever is inside goes onto the bottom, and the differential of sine is cos x, and that goes on top. And then a quick tidy up, dy dx is equal to 4 times 1, which is 4 over x, plus cos x over sine x. And you might remember that cos x over sine x is called cot x. It's in the formula books under trigonometry. Now, we're just going back to maybe work we did a few days ago. So what we have here is, it says find the value of the derivative of the following function when x is equal to 0. And what you had to spot was this is the product rule. So we've now got, for the product rule, dy dx, you should have learnt this by now, is the first function times the differential of the second function plus the second function times the differential of the first function. Now the first function is equal to 5x, and the differential of the first function will be equal to 5. Number 2, the second function is equal to e to the 2x, and what we discovered earlier on, that's when we differentiate an e function, it does not change, and then we multiply by the differential of the power, which is 2, which we then might write that as 2e to 2x. Now we can apply this formula. Dy dx is the first function. Well, what is the first function? The first function is 5x times the differential of the second function, which is 2e 2x, plus the second function, which is e to the 2x, times the differential of the first function, which is 5. We might choose to do a tiny bit of tidying up. So 5x times 2 is 10x on e to the 2x, plus 5 on e to the 2x. We were told to find the value of the derivative when x is equal to 0. So they're telling us to put x equals 0 and find derivative, which is another way of saying dy dx. So it's going to be 10 on 0 on e to the 0 plus 5 on e to the 0. Anything times 0 means it's 0, so that first one is 0. Anything to the power of 0 is 1, so that's 5 times 1. So the answer is just going to be 5. Now, we have to work this one out. It's a complicated one. So we've got y is equal to e to the 2x over 3x plus 1. So when we differentiate this, it's going to be dy dx. And what do we know? We know that an e function does not change. So it'd be e to the 2x over 3x plus 1. And then we multiply by the differential of the power. Ooh. So we need to know the power. What's the differential of the power? Well, the power currently is a quotient. It is a fraction. So if we are differentiating the power, then we need to do the bottom times the differential of the top minus the top times the differential of the bottom all over the bottom squared. So the bottom is 3x plus 1. If we differentiate the top, it's going to be equal to 2 minus the top, which is 2x, times the differential of the bottom, which is 3, all over the bottom squared, which is 3x plus 1 all squared. Tidying it up. 2 lots of 3x. Well, before we tidy up, let's rewrite it. It's 3x plus 1 minus, put the 3 at the front in front of the 2x. I brought both numbers to the front of the respective parts just to make it a bit easier. 3x plus 1 all squared. Now we work it out. 2 on 3x is 6x. 2 on 1 is 2 minus 6x all over 3x plus 1 all squared. Now 6x minus 6x, they cancel each other out. So what we're left with is 2 over 3x plus 1 all to be squared, and that's the differential of the power. So we come back up here, we've got dy dx is equal to e to the 2x over 3x plus 1 times the differential of the power, which is 2 over 3x plus 1 all squared. Now, it says find the equation of the tangent to the curve at x equals 0. So the first thing is, if we're looking for the equation of a tangent, then we're going to be looking for the equation of a straight line. If we're looking for the equation of a straight line, then we need to know its slope. And this is the slope function. So we will need to find the slope when x is equal to 0. So we're now going to have 2 times 0 is going to be 0, and 3 times 0 is 0, plus 1 is going to be 1. and here it's going to be 2 over, well, 3 times 0 is 0, so it's going to be just 1 to be squared. Now e to the 0 is 1, so dy dx, e to the 0 is 1 times 2 over 1, so dy dx is equal, quite simply, to 2. Now, I am running out of space, so I'm making the assumption that you've copied everything down. So what I can do now is I can rub out the bit on the right and carry on with the work. Now, they asked us to find the equation of the tangent. Find the equation of the tangent to the curve. The equation of a tangent is given by the formula y minus y1 is equal to m on x minus x1. Well, we know what x1 is. They told us x1 is equal to 0. We know what the slope is. The slope is equal to 2 because we just worked it out. So the only thing we don't know yet is the y1. So let's work out what y1 is. So at the moment, all we know is that y is equal to e to the 2x over 3x plus 1. And we know we're looking for the y value when x is equal to 0. So the y value when x is equal to 0 is e to the 2 on 0 over 3 on 0 plus 1. So 2 on 0 is 0, so it's e to the 0 over 1, and so therefore y is equal to e to the 0. Anything to the power of 0 is equal to 1. So we've now got y1 is equal to 1. So quoting this formula, y minus y1 is equal to m on x minus x1. And we're going to get y minus 1 equals 2 on x minus 0. So y minus 1 equals 2x. So y is equal to 2x plus 1. Not an easy question. Top grade A. It really is. I think that's the end of the examples. Yes, it is. So you need to get on with the questions that I set on the very first page. Good luck. 2 days.